Hello chaps. Ever wondered how to make Pong in x86 assembly and have it run without an operating system? Probably not, but today is your chance. I have done as such and would like to share with you what I have created, and then I'll talk a little bit about how it works. Here it is running in QEMU, which is a virtual machine environment. You can see I can move the two paddles up and down using W, S, J, K, and when the ball gets through the score is incremented. Pretty groovy stuff if I do say so myself. Shall we take a peer inside to see how it works? So before we look at the code, let's understand how and where it is actually running. In the old days everything was stored on a disk, and these disks were made up of segments about 512 bytes. When the computer booted, the first of this segment would be loaded into the hexadecimal address 7C00. This may sound weird, but BIOS can write into lower addresses and we don't want that overriding our code. That would be bad. Each subsequent segment is loaded one after another, but we have to do this manually by telling the BIOS to do it. Now we are ready to look at some assembly code. I am using Intel syntax because I don't hate myself unlike AT&T syntax people. I am going to discuss parts of the code that I think are interesting and skip bits that aren't, or I just can't be bothered to explain it to someone like you. That was a joke. The first two lines are not actually assembly code but rather directive that the assembler needs to tell it how you want it to treat the assembly. The first line org tells the assembler where the code is going to be located when it is running. This is important because when the assembler evaluates the jump address it needs to know where the code is, otherwise it will just jump to some random location in memory and nothing will work, and in these circumstances one would be very sad. Next, this tells the assembler what mode we are compiling for. When the CPU boots, at least when using legacy BIOS, it will always start in 16-bit mode, otherwise known as real mode. This imposes some limitations on us. For example, we cannot use 64-bit registers, although we can use 32-bit registers. The reason I chose not to move to 32-bit mode or 64-bit mode is because we can no longer call BIOS functions. One would have to program port stuff on one's own, and that takes time for no great benefit. Hence bit 16. There is a big list of data. This is important when trying to run the code on real hardware. This is often missed out in other tutorials, so remember to include it and save yourself from having to fix a very tricky bug to find. Global variables. These variables are defined as part of the code, so I must be careful to make sure execution jumps over them, as I don't want to execute them by accident. The D means define, and then there is either a B for byte, W for word aka 2 bytes, and then D for double word or 4 bytes. The EQU here means compile time value. The assembler will copy and paste these numbers in wherever they occur in the code, so they don't actually exist as part of the machine code. I realize now that using Blender to display code is rubbish, so here are bits of it shown from VS Code. The first few lines moves the value 0 into all of the segment registers. If you don't know what a segment register is, it is basically an offset to another register when reading or writing from memory. They are there because 16 bits only lets you access about 65 kilobytes of memory. The offset is 16 times the value in the segment register plus whatever is in the register you are using. But for this program it does not need to access larger address, so we can just set them to 0. One cannot directly write into the segment registers, hence why the X register is used as intermediate. The instruction CLD follows. There are some instructions designed to operate on strings. The direction flag tells the CPU whether the strings are stored in reverse or not. We want to make sure this is set to 0, meaning strings are stored as normal. When the BIOS boots, it writes the ID number of the boot device into the DL register. One needs to store this so that when reading the rest of the program the program reads from the same device that it booted from. Next just calls a print function I wrote, which displays a string to the screen using BIOS interrupt calls. This is bog standard stuff, so I won't go into detail. The next few lines loads the rest of the program, and then the jump instruction moves to the first of these segments. We essentially ignore the bootloader once the rest of the program has been loaded. This is because at the end of the bootloader there are 2 bytes called the boot signature. This tells the computer that the drive is bootable, and without them one cannot boot the program. Because they are at the end of the segment, they could overwrite our code as we make the program longer. For this reason, it is easier just to jump to the new segments and not worry about this, even if a couple 100 bytes of memory is wasted. Just a quick look at the read function. I'm not going to go into too much detail about what each of the registers mean, because finding that information online is trivial if you want to write your own. You can notice that being able to use BIOS calls makes this much easier than using ports. The last two lines are what sets the boot signature. The line with times in pads the rest of the bootloader with 0, and after that the last 2 bytes of the 512 byte segment are set to the special value. Now we are looking at the Pong code. The first 2 lines are similar to the bootloader. It is very important to note that it says 0x7E00 and not 0x7C00, as this code is located 512 bytes after the bootloader. Here are some global variables. Anything with the % is a preprocessor instruction like in C++. The drawcode.asm file contains functions for drawing to the screen. One can use BIOS interrupts to draw pixels, but this is slow, so to get better performance one can simply write directly to the screen buffer. Although it is important to use 2 buffers, because you want a buffer that you are in the process of rendering to and a buffer which only shows the finished frame. This is called double buffering, and if you don't do it you'll get screen tearing. That's a top tip, don't be like me. The first line of main uses BIOS to set the graphics mode. There are many different types of graphics modes, each with different color palettes and resolutions. Let me know if I should do a video on all of these. Next, it allocates a list of booleans for every key on the keyboard. This is so I call a function which gets key presses and writes to this array, and then for the rest of the program I just need to index this array, which makes it simpler. Important to note that the stack grows from higher address to lower address, i.e. downwards. That's why we could place the stack where the bootloader starts, because it grows downwards and will not overwrite the bootloader. Let's take a quick look at some of the drawing logic. This function sets the buffer to 0. When one XORs a register with itself, that is a marginally faster way of setting a register to 0. Remember, in the bootloader, the instruction CLD. Here is where that is important, because we are using the instruction repstosp. This is basically like memset in C or C++. Lastly, let's take a look at how I implement it to scores. To do this, I draw all the digits using a tool like LibreSprite. I then wrote a Python script that would load them using the PLO library and create a .bin file where each byte represented the pixel's color. Remember that VGA color palette for mode 13 means that you don't have RGB colors, but rather have to pick from 255 predetermined color. So the Python script needs to take the RGB value and find the closest color in the color palette. Once that is done, I can use the preprocessor to load the .bin files into the code and set a label for the start of each image. I store these labels in a list which I can index. The last line just pads the file with 0. I believed I have coded the most important parts. Let me know what you think. The code is on GitHub.